Hello, Bio 30. This is part 2 lecture of Hardy-Weinberg equilibrium questions. So as promised, I'm actually going to do some Hardy-Weinberg questions today. We're going to use this equation to solve some questions. I'm going to point you towards a few assignments that I've posted in the content section of D2L. So there's this assignment right here. It's in a landscape format, so it's a bit hard to see here, but these are Hardy-Weinberg questions, and I've actually posted the answers as well, so you can work through those. So you have, there's 10 questions here. But I'm going to show you that I'm going to do a couple of these questions. Maybe I'll just put my computer like this. I'm going to do a couple of these questions on my board, but I'm going to leave these questions for you to do as practice. There's a few of them that you can't do and they're not necessary to do. So I'm going to show you which ones those are. You don't need to do question 8 here. It's just unnecessary math that we don't need to do. I'm actually going to do problem 7, and I'm going to do a few questions. I'm going to do all the questions that are Hardy-Weinberg style in your key. You also don't need to do problem 11 and problem 12. All right, so questions 8, 11, and 12, not necessary in the Hardy-Weinberg questions that I've posted. And you have Hardy-Weinberg answers as well in this document. So it gives you an explanation as to why different answers are what they are, okay? So we'll leave it at, I'll leave those questions for you to do and read through on your own. I'm actually going to start my lesson with some questions with your key. So the biggest thing with Hardy-Weinberg, where students go wrong, is understanding when you're given a question, are you given a genotype frequency or are you given an allele frequency? So that's once we get there, this is not a hard concept to understand, but I'm going to give you some tips and some things like that that will help you understand what you're being given in a question. Because the math is repetitive and it's pretty straightforward. Knowing what you're being given is the biggest thing that you're going to see. So some other things that you might see with Hardy-Weinberg questions. Is you'll see this term abnormal allele. All right. So you'll see this the abnormal allele. So this is going to be, so when we look at the abnormal allele is going to be the recessive allele. Okay, and in the Hardy-Weinberg equation, Q is always the recessive allele, P is the dominant. It doesn't matter what letter we use to represent dominant and recessive. P squared, 2pq, and q squared always represent genotypes. So p squared is always the homozygous dominant genotype. So two dominant alleles, 2pq is always a heterozygous, so a dominant and a recessive allele, and q squared is always the homozygous recessive individual. Anytime you see abnormal allele, it's generally going to be a recessive allele. So when it says the frequency of an abnormal allele or something like that in a question, most of the time it's giving you Q, and you can use that information to solve for other parts of the Hardy-Weinberg equilibrium pieces. Okay. Some other things that you're going to see, you'll be given phenotypes. Right, so let's say, for example, 1 out of 1,000 individuals in a population have cystic fibrosis, so have CF. Now, cystic fibrosis is a recessive trait, so you have to have 2 copies of a recessive allele. So you have to have little c in order to have CF. So you would be able to use this to be able to figure out how many individuals are little c. So 1 out of 1,000 in this case would be q squared. All right, so that would be 1 out of 1,000. And then I could do my math, solve for the frequency of 1 out of 1,000, right, which is 0.001, and that's my q squared. And then I can use that to solve for q, right? Q squared to q would be square root, right? So when you're given a recessive phenotype, you'll be able to determine the genotype. But here's the deal. Let's say you're given a dominant phenotype. You don't know the genotype unless they tell you, because there's more than one genotype that could have a dominant phenotype. Right? Big A, right? So you have homozygous dominant and heterozygous individuals. They will both have the same phenotype. We talked about that yesterday as well in the lecture. You might also see this term carrier. Okay, so carrier is a heterozygote. Okay, and that individual can carry the trait to the next generation, but doesn't express it themselves. Okay, so that's another thing that you'll see. You'll also see percentages. Okay, so something occurs with a frequency of, let's say, 6%. You can convert that to 0.06. So there's multiple ways that you could see things represented in these Hardy-Weinberg questions. So that's what I'm going to decipher today. Okay. So let's look at some problems in your key, and let's get to this right away. So, first question says, this is page 127, and I'm going to look at numerical response number 1. Okay? So, when we look at the question here, the question says, polydactyly, the anatomical abnormality of having more than the normal number of digits is a common physical abnormality in cats. While normal cats have 5 toes on their front paws, polydactyl cats can have only have 7 toes. This mutation is found on the dominant allele. So what that means is, so let's use P, okay, because it's polydactyly. So P would be a polydactyl cat. Okay, so P is polydactyl, and then little p is normal. Okay. So the mutation is found on the dominant allele, which means that all cats that are heterozygous, as well as those that are homozygous for the dominant allele, will exhibit polydactyly. So, numerical response 1 says if the dominant allele frequency is 0.02, what percentage of cats will be polydactyl? So there's a couple things that I want you to... So you have an abnormality, and it is dominant. So I would underline those two things. So the question is saying if the dominant allele frequency, so allele, so big P, is 0.02, and it's asking what percentage of cats will be polydactyl. So that would be the amount of cats that would be big P, and big P, little p. Okay? So the amount of cats that are homozygous dominant and the amount of cats that are heterozygous, because the big P allele codes for that. So, I said the most important thing about Hardy-Weinberg is understanding what's being given. So in the question says the allele frequency. So what we have here, now don't confuse P and Q for the P's and Q's that I'm using in the actual question, because I'm just using big P and little p because we have polydactyly. All right, the alleles are interchangeable. So it tells me that the allele frequency is 0.02. So P squared is the genotype frequency for homozygous dominant individuals. 2PQ is the genotype frequency for big A, the layer heterozygotes, and Q squared is the genotype frequency for recessive individuals. This is the dominant allele frequency, which is P, and the recessive allele frequency, which is Q. So we were actually given that. So that's 0.02. Okay, so we were given that. I can solve for Q from that, right? So I don't know what this is. So I know that I have 0.02 for P because that was my allele frequency. So Q is going to equal 1 minus 0.02, and Q equals 0.98. And the question asks for, what is the percentage of cats that will be polydactyl? So I have P and I have Q. Okay, so I have the allele frequencies. What I want to know is what genotypes will be big A, or big P, and which ones will be big P, little p. So what I can do is solve for P and Q from here. So I have, right, so I can go up to P squared, and I can take P and Q, and I can do this math. So when I look for the amount of cats that are big P, and it could be big P, or big P, little p. That's what we're looking for. I'm going to use my Hardy-Weinberg equation. And I'm going to use P squared, so that's going to be 0.2 squared plus 2 times P, which is 0.02, times Q, which is 0.98, and that will give me the percentage of cats that are polydactyl, because it's a dominant allele. So let's use my calculator and solve for that. Okay, so 0.2 squared is 0.04. Right, 0.04 plus 2 times 0.2 times 0.98. Which is 0.0392. 0.0392, so I add those two together, and I've got plus 0.04 so I have 0.0792. And they wanted me to express that as a percentage, so about 8%. So approximately 8% of these cats will be polydactyl. Okay. And that's the first Hardy-Weinberg question that you guys need to know. And I need to make a quick correction here. Sorry. This is point. This is 0. I knew I made a mistake here. This is 0.02 squared, and this is 0.004. And that is point 0.0396. My bad. And so, well, we're about 4%. Okay. So just a quick correction there. So 0.0396 is the answer. Multiply that by 100 to turn that into a percentage, and we get about 4%. Okay. So that's numerical response 1, about 4%. Okay, so the Hardy-Weinberg principle allows population geneticists to quantify, we're looking at the gene pool, so what genes exist in a population. So that's question B. Let's look at page 128. So we'll use this equation again. And let's look at the next question. The next question says, it's a little hard to do this solo flipping through a workbook. My apologies. But Pendred syndrome, this is a numerical response 2, is a genetically inherited autosomal recessive disease. So I would highlight that, autosomal recessive. So in order to have being recessive, if I look at, again, big P would be non-Pendred in this case. All right? If it's a recessive trait, then that means the recessive allele is actually the one that's going to give this individual the condition, right? So with the polydactyly question, the dominant allele actually gave the condition. In this case, it's the opposite. Okay, so what happens with Pendred is the individual has deafness and decreased thyroid gland function. So the syndrome is thought to affect 0.008% to 0.01% of the population and accounts for about 10% of all reported cases of deafness. So there's a bunch of percentages here that aren't necessary to use. So that's deliberately there to confuse you. So it says if 0.008% of people have Pendred syndrome, what is the frequency of the abnormal allele? So it's asking for the allele frequency. And the abnormal allele in this case, the abnormal allele frequency is the recessive trait. So what we're actually trying to find in this question, we're trying to find Q. All right, so that's what we want. We want Q in this question. So I'm going to use the exact same equation. I'm going to leave that up there, and I'm going to show you how we're going to manipulate it. So here's the deal. With the question, it says 0.008% of individuals have Pendred syndrome. So they express the trait, and it's a recessive trait. So they have to be little p, little p. Now the part of the equation that would be little p is q squared. All right, so this would be little p, because if you have one dominant allele, that means no Pendred. Okay, so they have to be little p. So I have 0.008% of the population That is Q squared. So what this question gave you was a recessive phenotype. So you know that if the trait is autosomal recessive, that the phenotype will be the same as the genotype. All right? That's not the case with the dominant trait, because you could have more than one, right? You can have more than one genotype that codes for a dominant trait. But if the situation arises where it's a recessive trait, it has to be homozygous recessive in order to possess it, right? So a recessive phenotype gives you Q squared. It gives you the recessive genotype. So what I need to do with this is I need to turn a percentage to a decimal. Right, so 0. So this is confusing because it's already in decimal form, right? 0.0, it's an easy thing to miss. So 0.008 divided by 100 gives me right? So gives me 0.00008. All right, so that's actually the frequency of the abnormal that have this genotype. So I actually want to go from Q squared to Q. Okay, so I know that Q squared, I know that Q squared equals 0.00008. And I want to find Q, so to do that, you square root. And that gives me Q. These cancel out, and then the square root of 0.00008 is going to be, so the square root of 0.00 and it's about 0.009. Okay, so Q is 0.009. All right. So the frequency of the abnormal allele is 0.009. Okay. And it said recorded 3 decimal places, so that should be correct. Okay. So that's NR2. Let's do the next question here. Question 3. This says cystic fibrosis is the most common fatal genetic disease in North America today. The disease is, again, so we've got this recessive trait. So I hope that you're starting to pick out a pattern here. So it's recessive, so that means that you have to be little c, little c. And I'm using C for cystic fibrosis. So you have to be homozygous recessive to actually possess the trait. If you're dominant, you don't possess the trait, but you could carry it if you're heterozygous. So you carry it onto your offspring, but you don't express it yourself. It's estimated that approximately 0.03% of children born in Canada have cystic fibrosis, while approximately 4% of the population are carriers. So what is the allele frequency? So it's asking me for allele. What am I given? I'm given a phenotype, so 0.03% of all Canadians have cystic fibrosis. So that means 0.03% are little c, little c. And it's asking me to solve for Q again. So I'm going to solve for Q with this question. So let's erase this. So again, I was given a recessive phenotype, and I can plug that into the recessive genotype of the Hardy-Weinberg equation. And it's asking me to solve again for, so I have this, and it's asking me to solve for Q once again. So little c is, if we go back to the question, 0.03%. It gave me the amount of heterozygotes, but I don't need to use that because I don't need to find anything with P. So 0.03%, and then let's change that to a decimal, right? So 0.03 divided by 100. All right, point. Move that decimal place over 2 places, 0.003. Now I'm doing this slowly just so we're all clear on what we're doing with our calculator, right? So I know that q squared equals 0.0003. So in order to find q, I turn q squared into q, square root, and the square root of 0.0003 is, okay, and the square root of 0.0003 is about 0.02. Okay. So that equals 0.02, or about 2% of all the alleles will be Q, or little c. So my answer is D. Okay. Number 4 is another Hardy-Weinberg question. So we've got lots of Hardy-Weinberg examples for you to work with. Okay, so a hitchhiker's thumb is a recessive trait. So again, recessive. And I'm going to use H for this. Okay, hitchhiker's thumb. So in order to have hitchhiker's thumb, you have to be little h, little h. Okay? So having this trait appears to have no effect on the function of the thumb. In Scotland, 14% of people surveyed appeared to have hitchhiker's thumb, while in Canada, 23% of people surveyed exhibited this trait. And it's asking me for, what is the allele frequency of the abnormal allele? So it's asking me for Q once again. Now there's more information than I need, and it's asking me for Scotland. So I don't need the Canada information. I'm just going to cross that out. And I know that 14% of people in Scotland have hitchhiker's thumb. So that means 0.14 equals Q squared, because that is little h, little h. So they gave you a phenotype, and then you assume the genotype. Okay, so let's do this over again. This is not as easy as doing it in the classroom. Let me be sure of that. Okay, so again, P plus Q equals 1.0. So I haven't erased this at all. I'm just using the equation over and over again. So with this question, 0.14 equals little h, little h. It's asking me to solve for the frequency of the abnormal allele. So solve for Q. So Q squared equals 0.14. And I turn that percentage, right? 14%, right, actually means 14 divided by 100. Right, so I changed that into a decimal. Okay, square root, Q is going to equal okay, 0.14, boom, 0.37. Okay, so my answer rounded is a 0.4. Okay. So that's 0.37, or approximately 0.4 for Q. Okay. So these questions are actually easier than the first question that you were given, because you were given an allele frequency and then had to solve for the quadratic function. For the last 3 questions, all you've done is square rooted Q squared. So again, recognizing what you're being given is the hardest part of Hardy-Weinberg. I can't stress that enough. The math is actually pretty simple. All right, so numerical response 3, another one says, albinism is a genetic trait inherited through recessive alleles. So again, if you're an albino, you are little a, little a. If you're big A, or big A, little a, you do not have albinism. So those who are homozygous recessive for the albinism allele lack pigment in the eyes, skin, and hair. The condition is known to affect rodents, fish, reptiles, amphibians, and humans. In human populations, 1 in 17,000 people exhibit characteristics of albinism. So the question is asking, what percentage of the population of humans are carriers for the albinism allele? So the question is actually asking what's the percentage of big A, little a? And it gives you little a, little a. So little a equals 1 in 17,000. And that is Q squared in Hardy-Weinberg. So this one is a really good question because it kind of takes you through all the steps to find out what is the percentage of heterozygotes. So here we go again. And I'm going to just wash my towel off here. Okay, so let's get her going again here. Okay, so I've got P plus Q equals 1.0, right? Little a. And the question told me that 1 in 17,000 are little a. And what it actually wants me to find is 2pq. So here's the process, okay? I can use q squared, and I can find q. Right? So q squared, and then I can find q from that. Okay? By square rooting. And then I can do this. I can find p from that because p is going to equal 1 minus q. Okay? And then, so from q, I can find p. All right? And then I have p and q, and then I can just plug that into pq. Okay? So quite a few different steps here. So from that, I can get 2pq, and then that will equal the amount of individuals that are that, which is what we're trying to find. Okay? So let's do it. First thing is 1 divided by 17,000.